Today, I'm going to talk about reflection. Reflection is when light bounces off of a surface. This is opposed to light being absorbed or refracted. If the light is absorbed, the surface gains the light energy. If the light is refracted, the light passes through the surface, possibly being distorted as it does so. While absorption is probably intuitive, refraction deserves its own video. When light is reflected, there are two possible options. If the surface is smooth, the reflection is specular, or mirror-like. While if the surface is rough, even at a microscopic scale, the reflection is diffuse. In diffuse reflection, the light still bounces off, but it is now scattered, distorting the image of the original object the light was coming from. Objects actually gain their color from a combination of diffuse reflected and absorbed light. The wavelengths of light that the surface reflects indicates the colors of light our eyes see. The light we don't see is absorbed. Similarly, the transparency of an object is determined by how much light refracts through the surface. The more light that passes through, the clearer the surface is. While all of this is interesting, I'm going to focus on specular reflection and its relation with mirrors. An ideal mirror has all the light reflect specularly. None is absorbed, refracted, or diffused. As such, mirrors don't filter out any wavelengths of light, and thus have no real color. They simply take on whatever color light hits it. Now, there are three basic types of mirrors. The plane mirror, which is just the standard flat mirror, and two types of spherical mirrors, concave and convex. Concave is where the mirror curves toward the object. Convex mirrors curve away. Every other type of mirror can be approximated as one of these, or is made up of a combination of them. Funhouse mirrors, for example, which make objects look all distorted, are made of several spherical mirrors. For reflection, there are three main components: the object, which light bounces off of, the mirror, which reflects the light, and the image, which is where the reflected light reforms. We can actually find the location of the image by following the paths of light from the object to the mirror and seeing where these paths combine. For this reason, we always need to follow at least two paths for the light, to see where they intersect. For this, we note that when light is traveling, it will travel in a straight line, and when it bounces off the mirror, it obeys a principle called Snell's law. In the case of mirrors, this means that light will bounce off at equal angles with respect to the normal line. The normal line is the line sticking straight out of a mirror, perpendicular to the surface. Knowing this, we can quite easily find where an image is located if we have an object in front of a plane mirror. We simply draw two lines from the object directly to the mirror. However, we note that when they bounce off of the mirror, the light paths are now going away from each other. For this reason, we need to draw the virtual path of the reflected light beam to find where the light intersects. Since we had to use virtual light paths, which are paths of light where the light doesn't actually go, the image is virtual. This makes sense because when you look at a flat mirror, the image always appears behind the mirror. And since light doesn't actually go behind the mirror, the image is virtual. This same principle of light reflecting off of surfaces at equal angles with respect to the normal line applies to spherical mirrors as well. However, unlike plane mirrors, it is much more difficult to use any random light path because the normal line keeps changing directions. Luckily, there are 4 easy-to-use light paths that apply to spherical mirrors. However, before we get started, I should introduce the concept of the axis. This is a line perpendicular to the mirror that passes through the center of the mirror. The axis isn't a real line, in fact its creation is somewhat arbitrary, but it makes the mirror easier to analyze. The first of the light paths involves something known as the focus. It is found that any light coming in parallel to the axis will bounce off the mirror and pass through a point, known as the focus. It is called the focus because all light coming in parallel to the axis gets focused to this point. This is our first light path. Now, the reverse is also true. If light goes through the focus to the mirror, it will then reflect off so it goes parallel to the axis. This is our second path, from a point on the object through the focus. Now, because this mirror is spherical, there is a center point. A property of the center point is that any line that goes from the center to the mirror will hit perpendicular to the mirror. This gives us our third path. Since this line from the center point is perpendicular to the mirror, Snell's law indicates it should reflect back along the same path. Light goes from the object to the center point, bounces off the mirror, and returns along the same path. Now, do not confuse the center point with the center of the mirror, which is a point actually on the mirror. Our fourth and final path utilizes the center of the mirror. Since the axis is perpendicular to this part of the mirror, any light coming in to the center at an angle will reflect back out at that same angle. With this, we have 4 paths to the mirror to find the image. We only really need 2, and 3 are often used just to make sure you got it right. So with 4, we have choices. Just use whatever paths are easiest. These 4 light paths apply to both concave and convex mirrors. For concave mirrors, there are 3 basic results, while convex mirrors only have 1. The first situation is if the object is behind the center point for concave mirrors. To find the image, we just draw our 4 lines. 1 parallel to the axis and reflecting through the focus, 1 through the focus and reflecting parallel, 1 through the center point, and 1 reflecting off of the center. From this, we find the image located somewhere around here. Now, the specific positioning and height of the image depend on the position and height of the object, but we can use 3 general terms to describe it. It can be upright or inverted, real or virtual, and larger or smaller. Since the image is now below the axis, it is inverted, and since the image is where the light actually is, it is also real. Furthermore, the image is smaller. So, if an object is behind the center point for concave mirrors, it will always be inverted, real, and smaller. Now, if we place the object between the center point and the focus, and draw our 4 paths, we see that the image is still inverted and real, but now it is larger. If the object is now moved in front of the focus, the image changes again. We see that the image is now on the same side of the axis as the object, so it is upright. However, now the image is on the opposite side of the mirror, making it virtual. And lastly, the image is larger. The same 3 ways of describing images apply to convex mirrors as well. To find where the image is located, we draw the 4 light paths. In this case, like the previous one with the concave mirror, we have to draw virtual light paths. After drawing the paths, we see that our image is virtual, upright, and smaller for convex mirrors. This is true regardless of where the object is relative to a convex mirror. We can also find the location of an image mathematically. For this, we use the equation 1 over the focal distance, f, is equal to 1 over the object distance, s, plus 1 over the image distance, s prime. The distances are measured to the center of the mirror, and positive lengths are in front of the mirror, while a negative length is behind the mirror. Due to this feature, real images have positive distances, while virtual images have negative distances. Our goal is to find the distance of the image from a mirror. To find that, we first need to find the object distance and the focal length. The object distance we can simply measure. The focal distance, however, is a bit harder to find. Luckily, we can relate it to the center point of our spherical mirror. The focal length is just half the center point length, also known as the radius. It should be noted that since the center point and thus the focus of convex mirrors are behind the mirror, they have a negative focal length. This doesn't change the equations at all, you just input a negative number for f with convex mirrors. With these two variables determined, we can find the image distance. We can also find the height of our image by determining the magnification. For this, we use the equation magnification, m, equals negative s prime over s, which also equals the image height, y prime, over the object height, y. Since we can just measure the object height, this tells us the image height. If the image height is negative, then it is below the axis, indicating the image is inverted. If y prime is positive, the image is upright. Additionally, if the image height is less than the object height, then the image is of course smaller, and vice versa if the height is larger. So, using these three equations, we can describe the position and height of our image. Note, we can also use these equations for plane mirrors. In this case, the center of the sphere for a plane is at infinity, which means the focal length is also at infinity. This means our 1 over f term gives us 0. So, with a bit of rearranging, we find the image distance is the negative of the object distance. We can then apply this to our magnification equation, which shows that the image height is the same as the object height. This is to be expected. Normal plane mirrors do not magnify objects at all. Nevertheless, hope you enjoyed it, hope you learned something, and see ya.